During GR?
Yeah. That was later.
Well, that's awesome.
Uh-huh. You were there for that, Caleb? On Thursday?
Yeah, talked about it.
Talked about what?
Wait, how did you actually go about that?
Huh?
How did you actually go about that?
Because I was there.
He was there.
Yeah, I was there.
I saw him. I got the evidence. Okay. So, yeah. I have no idea what we're going to talk about today.
Where's Matt?
Matt's in Seattle, and he asked me if we were going to do this last week. I was like, yeah. He goes, well, I'm not going to be there. I said, okay. But then he's insisted on being the one who sends out the emails. So then when he flakes and he's out of town, I'm just like, maybe we're not having physics X today. I don't know.
Yeah, but does anyone who regularly attends actually check the emails, or do we just show
Well,
up?
that's what I'm beginning to wonder. Like, did I overstress myself in sending out an email today? Oh my God, people are going to think we're not actually going to meet. Well, that makes me nervous because when I don't want to meet, I guess you're just going to show up and wait for me until I'm just eventually like,
It didn't even cross my mind until you emailed. I was like,
I just
oh, yeah,
imagine
that
you
wasn't
all like
set.
outside the door. Shut. Kick the dirt. No, I'm just kidding. Okay. So we're all right. Let's talk about some stuff.
Something, probably.
Yeah, that's awesome. Sweet. Okay. So there's a couple of things. So there were some notes that I had from like last time that I didn't get to, but then I'm trying to figure out what to do first. Let's do these first. Why not? This will be fun. Okay, so ultimately we have this statement that's part of the statement of conditions for Calabi-Yaus. But in order to even begin to be able to make the statement, I have to introduce you to some math tech called fiber bundles. And fiber bundles they sort of start off seeming like this sort of really cute way to formally treat some interesting little spaces, and we'll talk about those simple examples. But they actually end up being incredibly important and very powerful mathematical tools that get applied a lot in physics, whether you realize it or not. So I'm going to kind of do this in a somewhat formal way to start, and then we'll kind of see the details in the course of an example. So consider, and I'm going to lean heavily on language that we've been developing in GR, but if anybody has a question about something I say, words they don't understand, just let me know. So consider three differentiable manifolds. And that word manifold is a loaded word. E, M, and F. Where this E is something I'm going to call the bundle space. This M is what is going to be called the base space, and this F is what is going to be called the fiber space. And what we have in mind is just sort of a working picture of a fiber bundle is that you have this base space M, which can certainly be more than one-dimensional. It could be, 5, 6-dimensional. But we'll just call that M, and remember, it is itself, by itself, a manifold. And then at each point on the base space, we have attached a copy of the fiber space, which I'll usually just draw as something like that. Again, the fiber space doesn't have to be one-dimensional. Obviously, drawing these things where these are multi-dimensional is hard. But of importance is that there's a copy of the fiber space at each and every point of the base. Obviously, that's a dense thing. I can't draw it because it'd fill out the board. But that's roughly the picture. And then this just continues. And then the totality of this whole thing is the space E. Okay? So just as a simple example, if M is in fact a one-dimensional base, so this is like some line, and then the F's are one-dimensional, then the total fiber bundle space E would be two-dimensional. Okay, just add the dimension of the base and the fibers. Okay. Now that in and of itself is a pretty vacuous definition. So we've got some important features that come along with the formal definition of a bundle. We have, first of all, a projection. And I'm going to start by saying things which are true for every bundle, and then I'll talk about some specific categories of bundles where I'm using that word category in the colloquial sense, not in the formal mathematical sense, because the last thing I want to do in any class is get into category theory. But we have a projection where if we take any point in the entire fiber space, or sorry, in the entire bundle space, and apply the projection pi, it gives us the corresponding point in the base M. So let's just give you an example of what I mean. Okay, so let's imagine that I close my eyes and I pick a point in the fiber, in the bundle space E. That means all I've got to do is land somewhere in this big oval. So there, okay? So if I pick that, wow, I landed on a fiber. That's pretty awesome. Yeah, pretty good, ain't it? So now if I pick that point and I apply the projection pi to this point, then I'm going to get back the corresponding point in the base, P, from which that fiber is sort of extended. Now, clearly this is a many-to-one mapping, because if I pick a different point in the same fiber and apply the projection, I get the same point P back. Okay? But if I pick a point that in the bundle that happens to be in a different fiber and apply the projection, then I'll get a different point in the base P prime.
Someone tried to open the door.
Is that Sarah?
No.
Oh, somebody. Oh.
A different person is not.
Okay. So we have this notion of a projection. And that, as a technicality, has to be a surjective now. We also have a Lie group, G, which is called the structure group. Which acts on F from the left. Okay. And the notions of left multiplication and even right multiplication might seem a little weird, but I think there's a particular category of bundles which I think will make it clear, but I'll just go ahead and say it. If your fiber was something like a vector space, so maybe your fiber was R2, so you have like X and Y, you know, this is the fiber, okay? Then you can imagine that you take elements of this and then you could rotate them with some transformation matrix R. Okay? So if I pick an element of this, then I can imagine that's like a little vector. And so I rotate the vector. The rotation matrix is this thing here, which I'm going to call the structure group. And it acts from the left. It acts on the vector. Okay? Where in this case, the vectors are the fibers. Okay? So that's what I mean by left multiplication. And there's a case I'll talk about in a few minutes where you can also define right multiplication. But left multiplication is sort of our natural thought of how matrix transformations act on vectors through linear representation. Okay. And then we have an open, and here you're going to start hearing some language which is reminiscent of language we use to talk about manifolds, but it's a little bit different. We have an open cover, so we have some set of open neighborhoods UI of the base. Remember, the base is the space M. So I have in mind that I take my base and I take little open neighborhoods of it, and they can overlap. So I can have like a U1 and a U2 and a U3. And then just like we talked about a little bit for manifolds, the idea is that you want an open cover, which means that you want to, if you take all of the UIs together, you get all of them. So this is part of what we talked about in defining an atlas in general relativity. So I have an open cover of the base with a diffeomorphism phi, which carries the direct product of one of the neighborhoods crossed with the fiber into the inverse of the projection map acting on that neighborhood of the base, such that pi compose phi so pi compose phi I. Phi I is labeling which diffeomorphism I'm talking about carries P and the value in the fiber F and returns me the point P, which is contained in the base. Okay, so this is very technical speak, but let me give you an idea of what this means, and this will make even more sense when we look at an example. What this condition here basically means is, if I take my bundle and I cover the base with all of these little overlapping neighborhoods, okay? And then I just focus on one of the neighborhoods. So maybe I focus on the U2 neighborhood, okay? I can take the U2 neighborhood, and of course it has these fibers that jut out of it. And there is a sense in which if I just focus on that, then I can view this as trivially U2 cross F. That is, it is just a direct product of one space with another space. Now that in and of itself might seem like, well, isn't that what the bundle is? It's like the base crossed with the fibers. I'll show you in examples why that's not a statement you can make more globally. But all this is saying is that we essentially have what's called a local trivialization. That is, if we just focus on a little neighborhood of the base, then we can consider that region of the bundle space to be a direct product of that piece of the base with the set of fibers over that piece of the base. And again, the difference, the distinction, and the importance of that will be borne out in an example. And then the last technical condition is that on every non-empty overlap between two of the U's, so e.g. Ui intersect Uj, where there's actually a non-empty intersection, we require G-valued transition functions that we can define to be Tij, where Tij is given by the composition of the diffeomorphism for one neighborhood with the inverse diffeomorphism for the other neighborhood, such that phi I can be obtained from phi j just by the application of the transition function. So again, I'm giving you a lot of formal definitions, and hopefully I'm going to give them a little bit more substance when I look at an example. Okay, so first of all, let me make sort of a statement about this, which is trivial bundles okay. If we can cover M with one UI, that is, if we only have one UI that we can use to cover the entire base in the bundle, or if all of the Tij are trivial, that is, all of the transition functions are literally just the identity operation. They don't really do anything interesting. But of course, the identity is always going to be an element of a group G, then E is trivial, i.e. E is literally just M cross F globally. Okay? Now notice up here, when I talked about the local trivialization, I said that you can take this little neighborhood and you can write the neighborhood as the neighborhood in the base cross F. What I'm saying is for a trivial bundle where the whole thing is trivial, you don't just have to restrict that to a little neighborhood. You can actually say it's the entire base times F. And that's what we call a trivial bundle. Okay? Trivial bundles are boring. We tend to do a lot of physics on them. Their boring features actually give them a lot of really nice symmetries, and you can actually do pretty much anything you want on a trivial bundle. But where things get really interesting are when you talk about non-trivial bundles. So to illustrate a non-trivial bundle, let's actually just look at a concrete example. Okay, any questions so far? I know I got my back to you a lot because I'm afraid you'll ask me hard questions. That's if I turn around. Never mind, doesn't matter. Okay, so let's consider an example. And this is the example everyone gives in their first course on fiber bundles. Let us consider a base space M, which is just a circle, S1. And we'll take the fiber space to be, we'll take the fiber space to be elements Z of the interval from -1 to 1. Okay, so Z is a line segment, basically. So, now, we have two possibilities in this case. So, possibility one is we take the total space to be a trivial bundle. Go ahead.
Is Z a line segment or a point on a line segment?
It's a line segment. So it's all the values on the real line between -1 and 1, including -1 and 1.
Yeah, so wouldn't it be a point on that line segment?
No, Z.
Because Z is an element of that interval, right?
I don't have a good. I don't. So sorry. Maybe this will make you happier. The set of Z's.
Oh, okay.
Which take values on -1 to 1. I don't have a good notation for a line segment. Like, I don't want to write R1, because R1 is all the way up to infinity. So, I mean, there's probably some standard notation for a line segment. It's just escaping me. Okay, but we have two possibilities. And the first is that we can take this to be the trivial bundle. So we can say that this space is everywhere, basically, and I'll just notate it like this, S1 cross a line segment. Okay? This is a space that you're all very familiar with. What do we call it? Think of a circle.
A cylinder?
It's a cylinder. It's exactly just a cylinder. So take a circle. That's your base. And at every point on the circle, you add in a line segment. And then you do this at every, and it's literally at every point on the circle, which of course becomes very difficult to draw. And then if you take the union of all of those, you've got the surface of a cylinder, and it's finite in length. Okay? And you could, if you wanted to, break this circle up into little neighborhoods. And what you would find is on any of the overlaps, if you ask, how do I get from this fiber to this fiber? Well, you don't do anything. There's nothing. It's a trivial map. Okay. It doesn't have to. Well, man, my phone is just blown up. Shit. Okay, so now let's do something non-trivial. So now let's take S1, and I can't write it in this simple way, but let's take S1, And let's break it up into two neighborhoods. So I'm going to take my S1 like this, and I'm going to break it up into two neighborhoods that overlap on each end. So I have a U1 over here, and I have a U2 over here. Okay? And then in each of these, I have a line segment, because this is now just a line segment without the ends. And then I have all the fibers. And then I have the second segment with its fibers. Okay? So these two ends are this overlap up here, and these two ends are the overlap down here. Okay? So then what I can do is on one overlap, I can use my transition function to be trivial. That is, just use the identity. But on the other overlap, I can use a slightly different transition function. I can use a transition function which maps the value of z from one neighborhood to the value of minus z in the other neighborhood. Okay. So what I'm literally doing is I'm taking a circle, or I'm taking a cylinder, and I'm cutting it here, and I'm cutting it here, and then I'm taking this cut, and I'm literally just gluing it right back together. This cut, before I glue it together, I'm doing this. What does that make?
The Mobius strip.
Exactly, that makes the Mobius strip. Okay. So the Mobius strip and the cylinder are both what we would call line bundles over S1. The difference being that the cylinder is a trivial line bundle over S1, and the Mobius strip is the non-trivial line bundle over S1. Okay? Okay, and similarly, if you want to talk about the Klein bottle, then you're talking about a circle bundle over a circle. Okay? But we're not going to get into that. Now, at this level, when I said trivial bundles allow us to do a lot more things, it's because they're kind of like, you get a lot of use in physics out of working on sort of restrictive spaces. Because, for example, in really trivial settings, you can kind of put any kind of physics on it you want. It's like it's just a free-for-all orgy of any idea you want to throw at it, okay? The more non-trivial various bundles become, the more careful you have to be about what you put on the space. So for example, we know that the Mobius strip is a non-orientable surface. Okay? So any concept in physics which requires a well-defined sense of orientation, you can't put that kind of physics on a surface like the Mobius strip, okay, or the Klein bottle. Right? Similarly, there are spaces where, or there are non-trivial bundle type structures that will prevent you from putting spinors on the space. And we know that spinors are a very, very important part of almost all physics. And so you have to know something about the non-triviality of the space. Now you might be sitting here going, well, wait a minute, you talked about this one special example, and then you've got this nice picture, but really how powerful, how broad of a set of spaces are these bundles? Like, can everything be a bundle? And it turns out, first of all, there are lots and lots of geometries that can be realized as bundles. More than you might think. But there are two categories which I think are probably the most common in physics. Let me see. The two most common categories of bundles encountered in physics are the following. So, and again, this is the colloquial sense of category, not the technical sense. This will actually be three categories, but two specific ones. So the first category is when F is a vector space. So that is, you know, in the case of this little cylinder example that I drew for you, the line segment is not a vector space, okay? But we could imagine, you know, for example, taking R2 or just something that is a vector space and having that attached at each point to a space. When F is a vector space, we have a vector bundle, okay? And it's important in this note, in this definition, to note that you can have like a base space. I'm going to draw that, insinuating that it's a loop. You can have a base space which maybe has dimension n, and then you can have a vector space which is maybe m. Okay, there's no reason a priori why the dimension of the vector space and the dimension of the base space have to be the same. However, we have category 1 star, which is if F is a particular vector space, and that is the tangent space, then we have the tangent bundle. Okay. Often called TM. Where in GR, we were careful to define this notion of TPM, which is the tangent space at a point on the bundle, or the tangent space at a point in the manifold. But if I take the collection of all of those tangent spaces, then I'm obviously talking about a bundle, because I've got the space and I'm at each point adding a copy of this vector tangent space. So I've got a tangent bundle, okay? Tangent bundles, first of all, any manifold has a tangent space that you can define at each point, right? So for any manifold, you can talk about that manifold's tangent bundle, whether the manifold itself is a bundle or not, right? So I'm not saying here's a manifold, can I break it up into a base and a fiber? I'm saying here's any manifold you pick, anything, it doesn't matter. I'm going to now add fibers to it, but there are these naturally defined things called the tangent spaces, and I'm going to consider that whole bundle. It turns out that's a very, very interesting bundle to study, because depending on how non-trivial the tangent bundle of a space is, there are restrictions about what kind of physics you can put on that space. One of the things that we know from thinking about tangent spaces in GR is that anytime you want to talk about vectors, or tensors in general, you're talking about things that live in tangent space. So you have to be very, very careful about, you know, if you're trying to put physics that involves vectors or dual vectors or general tensors on a space, you need to know whether or not the tangent bundle of that space is trivial or if it's precluding you from doing something. There is another category of bundles which finds incredible use, and that is if the fiber is itself equal to G. What is G? G is the, where was it?
You're just about
Here.
Oh.
G is the, it's up here. It's the Lie group, which actually acts on the fibers. Okay? Now, if F is equal to G, first of all, it gets a new name. We have a principal bundle. Yeah.
So it's acting on itself?
So now we have this interesting situation where we still have the structure group, which acts on the fibers from the left, but the fibers themselves are these transformations. And so now we can also consider the transformations acting from the right. So now what I have in mind, and this is where I said we would contrast this, for a vector bundle, we think about taking an element of G, for example, like a rotation matrix, and rotating a vector. So this is the G acting on the fiber, okay? Here, what we have in mind is more like a rotation being composed with another rotation. We know we can certainly act on a rotation with a rotation, and what we mean by that is the composition of two rotations. So there's certainly a natural sense in which this can act on this. Okay? But what's cool is we also get a natural definition of right multiplication. That is, we can act on the fiber either from the left or the right, because you can compose the rotations and you can compose transformations on either side. Here it wouldn't make sense to define right multiplication. Okay? Now, principal bundles might seem a little more abstract. After all, what have we got? We've got like this base M, and then at each point in the base, we've got basically a Lie group G. Anybody know any examples of Lie groups? How about U1, SU2, SU3? Is that starting to sound familiar to some of you? This is what gauge theory in the Standard Model is all about. At each point, we have a copy of one of these Lie groups. If you have space-time, and at each point your fiber is a U1, so you have a U1 principal bundle, then you're talking about electromagnetism. If it's an SU2 fiber, then you're talking about the weak interactions, and if it's an SU3 fiber, you're talking about quantum chromodynamics, the strong interactions. Okay? All of what I said about whether the bundles are trivial or not carries over. For example, the idea of a magnetic monopole is simply a statement about whether or not the U1 bundle is trivial or not. If the U1 bundle is trivial, then there are no magnetic monopoles. But if I actually twist the U1 bundle in an analogous way to making a Mobius strip, then I can create a magnetic monopole. Okay? So there's a sense in which the half of Maxwell's equations, and I've said this before in various classes, maybe in here, but definitely in GR and particle physics, half of Maxwell's equations come from an action principle. That's the ones with the sources. But then the other half, the ones without the sources, they are actually statements about the electromagnetic geometry. They don't come from an action principle. They're not equations of motion. They are actually statements about the U1 bundle. And if you want to amend those equations to describe physics, electromagnetism on a non-trivial bundle, that's exactly adding in monopole source terms. Okay? So in all of this, what we've discovered is that Holy Hannah, by thinking about an arbitrary manifold and thinking about its tangent bundle, the language of bundles begins to tell us interesting information about the space we started with. Or we can take a manifold like space-time, add in gauge groups, and then this whole bundle story will tell us interesting topological properties about gauge theories, which are, of course, the basis of all the fundamental interactions in physics. Okay, so there's so much more I could say about bundles, but I don't want to dwell on it too long because I want to get on to something else. But I have to get to a certain statement before I can carry on. So yes. Okay, so a very, very crucial part of the bundle story, which I'm not going to mention, but it's essential, is the notion of a section. And the notion of a section is it's almost like a singular cousin to the projection, in the sense that if I think about a bundle, the projection pi lets me pick any point in the bundle, and it drops me down to the corresponding point on the base. Okay? What a section does, just to give you a picture of what a section is, what a section is it is a map that takes each point on the base and gives you a single point in each fiber. So a section is literally, you can think of it as like a curve that goes through the bundle space. Because if I think about this curve, it intersects each fiber at one point. And so this might be what I call the section M. And so if I pick a point in the base, the section just carries me back up to the point where this crosses it. Hence the name section. Okay? And sections become a very, very important part of analyzing bundles, and they actually become a very, very important part of using bundles in physics, because when we start writing down Lagrangians and actions and equations of motion, it's actually usually in terms of sections of bundles. So when we, for example, in electromagnetism, when we write down A mu of x for the gauge potential in electromagnetism, that's actually a section. Okay, so speaking of that, there's one more idea that I have to throw at you, and that is the notion of a connection. And the notion of a connection is actually a pretty straightforward one. To kind of pictorially talk about, it's really kind of technical to get to the mathematical definition of it. So I'll just give you the pictorial one, and then I'll tell you about some context where you've seen it. But we can imagine if we have this manifold M and we have some space here, then, and this is not necessarily the tangent space, but we can start talking about what does it mean to move along the fibers or transverse to the fibers? Okay, so for example, if I have a couple of fibers that are sort of right next to each other, and I go from this point to say this point, did I actually go from here to here moving only along M and not along the fiber direction? And notice I drew these wiggly intentionally, because if you kind of say, well, how far is it along the fiber from base? It's not quite clear. So, and also the way that I've defined the bundle in general, it's not even really clear, like, how do we compare a point here to a point here? Like, are those the same height? Like, what do I mean by height? Is there a measure of, like, how high up the fiber I am? Okay? So what we can do is we can introduce a notion of splitting verticality from horizontality in the bundle. So we have verticality and things which are horizontal. The idea being that moving horizontally in the fiber space means you're only moving in the directions associated with moving in M, and you're not moving up and down in the fibers. And then moving vertically means you're only moving in the fiber direction, and you're not moving in the base at all. Okay? Now there is a mathematical construction that you can write down that will formalize this, and it's in terms of what's called a one-form, and this is a one-form in the bundle, a one-form connection. So this is where the word connection comes in. It's basically a mathematical apparatus which formalizes this separation for us. And we denote that by the letter A. Okay? And if we are in the case of one star, then A is basically the gauge field in gauge theory. Or sorry, that's if we're in two. If we're in one star, A is the connection gamma, which we'll see in GR next week. It's called the actually no, we'll see it this week. It's called the Christoffel connection. Okay. Another way that you think about these things, which is the way that we introduce them in particle physics and the way that we'll introduce them in GR, is these things, these connections, are what formalizes taking the derivative of things. because we have to be careful, and we talked about this in GR a little bit. If we want to take the derivative of, say, a vector, vectors live in tangent space, and as you move around a space like a sphere, the tangent spaces at different points aren't the same. They can point in different directions. And so when you want to take a derivative, and remember a derivative starts by taking the value of a function or the value of a vector if you're taking the derivative of a vector. You're taking the vector at one point and the vector at an infinitesimally separated point, and you're forming their difference, and then you're dividing by the separation. To be able to formalize taking that derivative, you have to be able to know, am I moving in the manifold? Am I moving around in the fiber space? And so you can kind of sense the way in which these connections are connected, no pun intended, to the ability to take a derivative in these contexts. We're going to see that in gory detail in GR on Thursday. Go ahead.
So in that case, the fiber space is the tangent?
Tangent space.
Okay.
Yeah.
Okay.
So here, this case where these things are called the Christoffel connections, these are associated with the connections if you're talking about case 1 star where you're looking at the tangent bundle.
Okay.
Okay. All right, now I said all that so I can say this. There is, so you can ask yourself, okay, so if you just handed me a space and you asked, is this space a trivial bundle or not? Or what, how, is the tangent bundle of this space trivial or not? Then you end up wanting to calculate these things called characteristic classes. And these are basically things which are built from, for example, the transition functions or the connections on these fiber bundles. There's different ways to come at them. Okay, and there's different varieties of characteristic classes, but there's one in particular that I want to talk about, which is associated with these connections. And that is the following. I think it's hilarious because I was like, I had these 3 pages of notes, and I was like, 3 pages of notes are not enough to get through. So I went to my office, and I, like literally 15 minutes before class, I wrote a page and a half of notes. And I haven't finished that page and a half of notes yet, and we're 45 minutes in. This thing just, like, it's time dilation or time contraction or just, I don't know what the hell it is. Anyway.
Talk a lot.
Or I talk a lot. You say that with like a negative connotation. I don't think I appreciate it. One bandwidth. There is the notion of the Chern class, which we can define to be the determinant, and there's no motivation for this particular definition. But it's the determinant of 1 plus I over 2 pi times f, where f is defined in terms of the connection A, and remember A could be the A from gauge theory. These are the A's that we use in particle physics. Or you could be talking about the gamma if you're talking about the tangent bundle. Just depends on what kind of bundle you're talking about. But f is given by dA plus A wedge A. Remember A is a form. And so as per the lessons we've talked about in physics X on forms, I can define the exterior derivative of the form, and then if I want to multiply forms, I have to do it in this weird way called the wedge product, which keeps everything antisymmetric. But if A is a 1 form, then F is a 2 form. The exterior derivative raises the formness 1, and then I've got a 1 form wedged to the 1 form. So this is the 2 form, and this is called the curvature 2 form. Of the bundle. Okay. Literally, if you were talking about electromagnetism, like if you were doing a U1 principal bundle, where A was literally the A that you think of with the electromagnetic vector potential, then in that case, F is just F mu nu. It's literally that d mu a nu minus d nu a mu. Okay, it's literally the field strength tensor from electromagnetism. Okay. For the tangent bundle to a manifold, F is the Ricci tensor. Okay, and we'll see that in GR. I mean, there are people in the room who have taken GR, but we'll see that the Ricci tensor is a quantity that you construct out of derivatives of the Christoffel connections and then various quadratics in the Christoffel connections. Okay. And then this thing can be expanded into a set of terms where we have, and I think it's C0 is just the identity. And the higher order terms just tell us more refined information. But I think this guy is trace of I over 2 pi f. I could have that wrong. And then the higher classes get more and more complicated. And these are called the Chern classes of the space. And so a point that we will talk about later on when we come to the definition of Calabi-Yaus is going to focus on this thing, which is called the first Chern class of the bundle. Okay, so that'll play an important role in our final discussion on Calabi-Yaus when we actually get to formally define them. Okay? But the idea is basically, if I had a completely trivial space, like, here's a really trivial space, R2, where I can view that as either an R1 bundle over R1, or I can think about that as my manifold and then think about the tangent bundle over that. But again, that's trivial because it's an R2 bundle over R2. But this is just the most basic, thinking of this as a bundle or thinking of this as the base of a trivial bundle. That space is completely trivial, and all of these Chern classes would trivially vanish. Okay, the zeroth Chern class won't vanish, but all of these Chern classes will vanish. So there's a sense in which when you start constructing these quantities, they're actually measuring for you how non-trivial the bundle in question is. When things don't vanish, then the space is starting to get more non-trivial and more interesting. Okay? All right, so I'm going to leave behind formal speak about that for a minute. I don't know if I can't do this in 10 minutes. There's no way I can do this in 10 minutes. Yeah, I think I'm going to stop. Actually, let me see if I can elaborate. Well, I've got 3 pages, and I just got through a page and a quarter, and I don't want to rob this. God, I'm never going to get through this. It's Calabi-Yau. It's like the what is it? The thing that keeps receding from you. It's like chasing the horizon. You just keep running towards it. The horizon just keeps going away. That's kind of like what Calabi-Yaus are for us. I know what I'll fill you in on. My graduate student, my first graduate student, Casey, he talked about this, and he worked on a gauge theory of gravity. And did you guys see Casey's? Yeah, way back in the day he came to, I think, GR and gave a presentation. But if you want to talk about a gauge theory of gravity, then you actually run into a really interesting problem in this whole scheme. So first of all, you can ask yourself, is this machinery necessary? I guess that's like the first question you should ask. Like, here's some highbrow math. Do you really need it? Because you guys have been doing E&M. Like, you did Physics 200. You're going to go through intermediate E&M. You're going to go through advanced E&M. You're going to go through graduate E&M. And you're never going to talk about a friggin' bundle. So you can ask yourself, like, do you really need this? The answer is, well, if you ever want to understand E&M on a space which is topologically non-trivial, yes. Okay? Unfortunately, a lot of physics, well, not unfortunately, depends on how you view it, a lot of physics is set in the context of trivial spaces. Like, we always think of physics on infinite flat space. We don't worry about that there's an end, or that things are curled up into a circle, or that they're defined on the surface of a sphere. Clearly, though, you can construct condensed matter systems where things are confined to two-dimensional surfaces and then wrap those surfaces around on each other and make topologically non-trivial theories. If you want to, for example, address electromagnetism in those contexts, then you have to take these considerations into account. It turns out also that in gauge theories, you have the possibility of what are called topological defects. And topological defects are they're topologically non-trivial solutions to the gauge theories, but they present themselves. So, I mean, how many of you have heard of an instanton, a sphaleron? Okay, so yeah, I mean, these are. I'm trying to think of how. So I'm going to give you like poor man's topological defect. Okay, I'm going to just give you the poorest topological defect I could possibly give you, and just to make it incredibly concrete. So here's a string, okay, and it's an infinite string. The physics of the string is it's wildly entertaining. You can pluck it, and it will vibrate, and it will do interesting things. And maybe this string is living in this room, so you can pluck it in any dimension, and that's your physics. Okay, but. Or we could take the string and we could do this to the string, okay? And then we can imagine taking this and plucking it, and then it would vibrate and do weird things. But there's a sense in which this thing is not radically more interesting than this. Because there's a sense in which if I took this and I plucked all the points in just the right way, it would become that, right? You agree? Okay. But now, consider this string, where I come in from infinity, and I go out to infinity, but in between, I make a loop. And that's probably, now I'm, well, yeah. Actually, let's make it worse. And make a knot. Okay? Because I know what you're going to do. You're going to go, oh, that loop, you can just kind of twist it around and flatten it out. So we can't do that. Okay? So the idea here is I can still pluck this and get interesting physics, but you can't take this thing and continuously deform it by taking little pieces and moving them around back into the original trivial configuration. Okay? So this is an example of what we might call a topological defect. The only way to get rid of this is to take the whole thing and do something which goes off all the way to infinity. I mean, you can untie the knot, but untying the knot means you got to get the ends of the string and undo them. That's a topological thing. Okay. So all of this bundle language becomes important anytime you want to talk about how various physical theories behave on topologically non-trivial spaces. Okay, so what Casey wanted to do was, and people in the past have wanted to do this, they wanted to say, can GR be a gauge theory? And, the standard model, as we've talked about in Physics X, is based on this U1, SU2, SU3 gauge theory where, it's determined by all this principal bundle kind of stuff. But you can just ask yourself from the get-go, like, what would the gauge group of GR be? Like, if you're going to pick what the symmetry group would be, like, what would it be? And in the course of general relativity, as we build the theory of GR, for those of you who have taken particle physics, you're going to go, oh, that's kind of like what we did in particle physics. We're going to make a covariant derivative, okay? We're going to start with a non-interacting theory, and by making a local symmetry, get an interacting theory. The stories play out analogously, but what you discover is that the symmetry group in GR is, of course, the Poincare group in 4 dimensions, which is, sadly, the semi-direct product of the Lorentz group, which is, yes.
So 3 up.
Oh yeah, sorry, I said 3 up, thank you. The proper orthogonous Lorentz group. That's a little arrow pointing up. Crossed with translation. So these are just your good old rotations in 3 dimensions and then boosts along the x, y, and z axes. These, however, are the translations in t, x, y, and z. The totality of this, and this is this technical thing called a semi-direct product, whose definition requires words that I would then have to define, so we won't go there. But the entirety of this is the symmetry group of special relativity. And so if you wanted to make general relativity by taking special relativity and gauging the symmetries, then you would somehow want to be gauging these. Here's the fundamental problem, okay? Let's take space-time. So for example, Minkowski space in 4 dimensions. At each point in Minkowski space, we know we can construct the tangent bundle. And the tangent bundle is going to, in a sense, be spanned by t, x, y, and z. Okay? So there is a sense in which I could also imagine, so what operations would be the Lie group that acts on these fibers? So remember, in a fiber bundle, you always have to have that Lie group G that is the structure group.
Rotations?
Well, it's rotations in T, X, Y, Z. It's SO1, COM3. Okay? So that would naturally lead me to say, well, what about the principal bundle? Remember, the principal bundle is where you take the structure group and make it the fiber itself. So then I can imagine taking Minkowski space and then at each point attaching a copy of SO1, 3 up. Okay? And then you might say, oh, well, maybe that's like the equivalent gauge bundle for general relativity. But the problem is these guys, the translations. Because where we think about SO1, 3 as rotating in the tangent space, remember tangent space is defined 1 point at a time. Translations, by definition, move you in the base space. They translate you. But you can't think of this as motion in a fiber or an action on the fibers. It's actually an action on the points in the base space. So if you're, it's kind of obvious. I mean, it actually wasn't obvious. In the 60s, a lot of really smart people were trying to figure out, is GR a gauge theory? And the very first guy that tried it tried to just gauge SO1, 3, and he ended up with this really wonky theory. The Einstein-Cartan or the Cartan part of it. And he actually didn't gauge this, and then the smart guy came along and said, no, you actually got to gauge the translations. But anyway, no one really thought too hard about how you would actually do this with bundles. Okay? And so to do the bundles, it turns out, and there's only been a couple of people that have ever worked on this, you actually have to introduce sort of this new idea in bundles, and that is the idea of what's called a composite bundle, where you have your space M, and you have your fibers, but then off of the fibers themselves you have fibers. So obviously this becomes incredibly difficult to draw. Okay? And then what you have in mind is that the entire fiber here would actually be this semi-direct product. But then you encode the translational part of this gauge group with motion along these auxiliary fibers. And then the SO1, 3 is along the vertical part of these fibers. And then you also have these, you have projections, so you can take a point and you can project it all the way down to the base. So if I did the projection of this point, it would take me here, but you could do the partial projection to here. So these points would all get partially projected to here. Okay? And then you can think about this bundle as a result of these, and then you get this thing called the plateau, blah, 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 blah. But these composite bundles are sort of the best candidate for a bundle structure underlying general relativity, and that's what my first grad student studied. And he actually discovered that there are some very strong conditions there's some very strong topological restrictions on the space-time M. So what spaces are allowed in general relativity? I've said to you in the class that they have to be manifolds. That just means that locally they look like Euclidean space or Minkowski space, if it's a Lorentzian signature manifold. But I haven't said anything about globally. Like, can they be, curved back on themselves and closed up, topologically non-trivial? And so the global restrictions on spaces in GR is a much more open question. And so we studied this, and he actually came up with some interesting restrictions, among which it seems is that if these are the right bundle constructions for gauge gravity, you actually, the space has to admit what's called a string structure, which is a topological constraint that you find arising in string theory, which makes no sense whatsoever. Because this entire analysis is purely classical, there's nothing quantum in it. And string theory is the requirement that you bring into the story when you want to do a quantum treatment of gravity. Okay. I know that last bit kind of went, but I filled 12 minutes with it. So when we come back next time, I'm going to talk about what I was going to talk about today before I wrote that other stuff. And those of you who are in GR, and those of you who aren't GR will really appreciate it. It's very visual. And it'll get us to our final definition of a Kähler manifold, which will put us on the precipice of finally defining Calabi-Yaus. Okay. You got a question?
Yeah. So I don't know if I'm thinking about this backwards. One of the problems with trying to gauge GR is that there's no gauge boson. Or is that a consequence of the fact that it can't be gauged? Or has it been?
No, so so GR as a gauge theory is so the gauge boson of GR would be gravity, the graviton. Oh. So there's a well understood idea of what a graviton is and sort of a gauge theory of gravity. It's kind of weird because it kind of depends on your starting point. There's a certain sense in which if you think of GR as starting with flat space and then looking at small fluctuations away from flat space, then the theory, and if these fluctuations are small, then you can, basically, you can take the metric for the space and you can break it up into flat space metric plus small fluctuations. And if these are small, then that means you ignore things of order h squared and higher. Okay? And if you ignore the higher order terms, then you're dealing with what's called linearized gravity. And linearized gravity genuinely looks like a gauge theory defined on flat space. And in that theory, you work with it just the way you work with the standard model gauge theories, and the graviton is the gauge field. And so you can do all the Feynman calculations, you can do all the wonderful stuff we did in particle physics in this linearized version of the theory. And that's where you run into these problems with renormalization and so forth. Now, of course, that's a very limited starting point because not all space-time geometries are a small fluctuation away from flat space. The universe we live in is not. So deeper considerations of how you would quantize gravity have got to get away from this linearized starting point. But if you want to kind of talk about, remember when we do gauge theory and particle physics, a lot of times we're even looking at small fluctuations in, say, the electron field. We don't apply Feynman diagrams to people. We're collections of many things. We're very large excitations. You usually just take like a particle or two at a time and you do Feynman perturbative calculations. And so to the degree that you were trying to do the gravitational interaction between very small things, you could get away with this approximation. But if you want to actually answer, how does the whole enchilada work in a quantum context, then you've got to start with a different starting point, and there's a lot of philosophical debate about what that starting point should be. Even string theory is sort of born out of this perturbative starting point, although it does eventually get to some non-perturbative statements about gravity. So I say all of that, but in everything that I just told you, working with the gauge theory, that's not necessarily talking about the bundles. In the same way that you do electromagnetism and you don't talk about bundles. People can do gauge theory of gravity without talking about bundles. What we were looking at, which only a few people have really tried to look at, is what are the bundles that you would use if you were doing sort of a bundle treatment of gauge gravity? And that's where the answers are still a little less agreed upon. Other questions?
So do fiber bundles inherently have some sort of meaning, or are they more just a useful framework on which to do physics?
Give me an example of something that has an inherent meaning so I know what you're referring to.
So is there something that, like you say, you can go through all of this E&M without ever looking at a fiber bundle, so...
If you're not interested in certain questions, like if you want to know how would I do E&M on the surface of a sphere,
then this is required.
If my universe was, well, it might be required, but the thing is a lot of the physics that you do is set in a trivial space like R3 for E&M or M4. And on those cases, since the space is trivial, if you put the bundle machinery into it, it's not going to give you anything interesting. The bundle machinery is really going to yield fruit when there's some topologically non-trivial things for it to detect. So to the degree that you've never worked in a topological context, you would have never needed it. But as soon as you start working in topologically non-trivial contexts, for example, trying to do E&M on the surface of a sphere, or actually really getting into the meat of what a magnetic monopole is, then I think the bundle language is indispensable. People have talked about magnetic monopoles in the absence of the bundle language, but it's really hard to really appreciate the story of a magnetic monopole without this bundle thing. So the truth is, the bundle picture is the complete version because you want your... People would argue that a physical theory isn't complete unless you understand how it works in many different contexts, not just infinite space. Because truthfully, like, are we 100% sure of the geometry of the entire universe? Like, you just don't know. And you also are not 1,000% sure what the hell's going on inside of a black hole. So it could be that there's something topologically non-trivial inside of black holes. And yeah, we would have to go into a black hole to do the physics experiments to see the effects of the predictions based on bundles, but So if you want to know the truth, a lot of people are like, you need to understand how your physics works in all possible contexts on which it's well defined. Even if it's not, and trust me, we're gonna look at a geometry in GR where you're all like, well, why would you look at that? Because that can't happen. And I'm like, well, it doesn't matter. Like, the physics, the theory itself has to make sense on all of the geometries on which it seems to, on all the geometries that it seems to predict, even if it doesn't happen to be the geometry that we live in. So, otherwise you run into these logical inconsistencies. Like, if GR had a solution which was a geometry that GR couldn't work on, then GR is inconsistent, which it is, because that's exactly what a black hole is. Like, GR doesn't work in the singularity of a black hole. So the fact that GR predicts things which GR itself can't handle, it's a big problem with GR, and that's why it needs to get fixed with quantum gravity. Okay, so yeah, I mean that's my answer. Okay. You got another one?
Yeah, I think this will be faster. So
It'd have to be fast.
okay, so you say that we don't use these like simplifications to not have to use fibers, like in E&M, like how we're taught.
Uh-huh.
Is there a fiber representation of the E&M that we've been taught so far?
Is there a I mean, can you do all the E&M that you've been taught in terms of a fiber bundle language? Yeah, definitely. I mean, the gauge. So, first of all, you don't talk about E and B. You talk about A. So when you talk about E and B, you're not really thinking about E&M as a gauge theory. You're only talking about the gauge invariant quantities. But to really understand it as a gauge theory, you need to think about the redundant variables, the things that you describe it with, that you can transform and it doesn't change. So so at the end of the day, to really understand E&M as a gauge theory, you need to formulate it and work with it in terms of the gauge potential A mu. And I don't know how much of that you guys get. And A mu is, of course, the scalar electric potential and then the magnetic vector potential all lumped together into a 4-component, 4-vector potential. That A mu is formally the connection on a U1 gauge bundle over Minkowski space.
Oh, okay.
That's what electromagnetism is. It's a U1 bundle over. And what's cool, and I'll tell you another thing where this bundle language becomes really cool, is, and I could have actually kind of vamped about this when I was running out of time. When you have a space like M and you have these fibers like U1, you can ask yourself, well, why don't you just think of this as part of space-time so that the whole thing is space-time? Like, what makes the fibers so special? And there's a certain sense in the formalism in which there is a clear distinction between the fibers and the base. But then if you set it up right, there's actually it's not necessarily so important to distinguish them, because one of the things that you might realize very quickly is that U1 is really the set of transformations of shifts around a circle. Remember what U1 does? It basically rotates you in the complex plane. So there's a sense in which if you have a space with U1 fibers, you can kind of think of this as a space with circles. So now I would just make this a circle, appended at every point. A circle is just like a real geometric notion, and then I can say, well, what if this was my space-time? Is there some sense in which treating this as space-time is the same as doing electromagnetism? And the answer is yes. If I do M4 cross S1 and I do GR on that space, that's Minkowski space crossed with a circle, this is exactly the same as E and M in Minkowski space. That's what Kaluza-Klein is. So this is, for me, thinking of this in terms of the bundle languages is sort of a natural segue into Kaluza-Klein ideas, which is where you get gauge theories from general relativity in higher dimensions, the simplest case being electromagnetism by having an extra circle dimension everywhere, where those are just circle fibers over 4-dimensional Minkowski space. Your classmates are going to hate you. Go for it.
It's a quick one. So earlier on in GR, you were talking about how the space-time geometry we use in Phys 1 is like time with a copy of R3 at every point.
Yeah.
So would that be an example of this?
Yes. I was saying that was, yes, good job. I actually said it was an R3 bundle over R1.
I know.
Yeah. Oh, good job. All right, guys, I got to get downstairs to the GR class. I knew